Chapter 4. The Quantum Mechanical Evidence. Permanence unexplainable by classical physics. Thus, aided by the marvelously subtle instrument of X-rays, which, as the physicist remembers, revealed 30 years ago the detailed atomic lattice structures of crystals, the united efforts of biologists and physicists have of late succeeded in reducing the upper limit for the size of the microscopic structure. The upper limit for the size of the microscopic structure being responsible for a definite large-scale feature of the individual, the size of a gene, and reducing it far below the estimates obtained on pages 29 to 30. We are now seriously faced with the question: how can we, from the point of view of statistical physics, reconcile the facts that the gene structure seems to involve only a comparatively small number of atoms, of the order of 1,000 and possibly much less, and that, nevertheless, it displays a most regular and lawful activity, with a durability or permanence that borders upon the miraculous? Let me throw the truly amazing situation into relief once again. Several members of the Habsburg dynasty have a peculiar disfigurement of the lower hip, Habsburger lip. Its inheritance has been studied carefully and published, complete with historical portraits, by the Imperial Academy of Vienna, under the auspices of the family. The feature proves to be a genuinely Mendelian allele to the normal form of the lip. Fixing our attention on the portraits of a member of the family in the 16th century and of his descendant, living in the 19th, we may safely assume that the material gene structure responsible for the abnormal feature has been carried on from generation to generation through the centuries, faithfully reproduced at every one of the not very numerous cell divisions that lie between. Moreover, the number of atoms involved in the responsible gene structure is likely to be of the same order of magnitude as in the cases tested by X-rays. The gene has been kept at a temperature around 98 degrees Fahrenheit during all that time. How are we to understand that it has remained unperturbed by the disordering tendency of the heat motion for centuries? A physicist at the end of the last century would have been at a loss to answer this question, if he was prepared to draw only on those laws of nature which he could explain and which he really understood. Perhaps, indeed, after a short reflection on the statistical situation, he would have answered, correctly as we shall see, these material structures can only be molecules. Of the existence, and sometimes very high stability, of these associations of atoms, chemistry had already acquired a widespread knowledge at the time. But the knowledge was purely empirical. The nature of a molecule was not understood. The strong mutual bond of the atoms, which keeps a molecule in shape, was a complete conundrum to everybody. Actually, the answer proves to be correct, but it is of limited value as long as the enigmatic biological stability is traced back only to an equally enigmatic chemical stability. The evidence that two features, similar in appearance, are based on the same principle is always precarious as long as the principle itself is unknown. Explicable by quantum theory. In this case, it is supplied by quantum theory. In the light of present knowledge, the mechanism of heredity is closely related to, nay, founded on, the very basis of quantum theory. This theory was discovered by Max Planck in 1900. Modern genetics can be dated from the rediscovery of Mendel's paper by de Vries, Correns and Schwermach, 1900, and from de Vries' paper on mutations, which was from between 1901 to 03. Thus, the births of the two great theories nearly coincide, and it is small wonder that both of them had to reach a certain maturity before the connection could emerge. On the side of quantum theory, it took more than a quarter of a century till in 1926 and 27, the quantum theory of the chemical bond was outlined in its general principles by W. Heitler and F. London. The Heitler-London theory involves the most subtle and intricate conceptions of the latest development of quantum theory, called quantum mechanics or wave mechanics. A presentation without the use of calculus is well nigh impossible, or would at least require another little volume like this. But, fortunately, now that all work has been done and has served to clarify our thinking, it seems to be possible to point out in a more direct manner the connection between quantum jumps and mutations to pick out at the moment the most conspicuous item. This is what we attempt here. Quantum theory, discrete states, quantum jumps. The great revelation of quantum theory was that features of discreteness were discovered in the book of nature, in a context in which anything other than continuity seemed to be absurd according to the views held until then. The first case of this concerned energy. A body on the large scale changes its energy continuously. A pendulum, for instance, that is set swinging is gradually slowed down by the resistance of the air. Strangely enough, it proves necessary to admit that a system of the order of the atomic scale behaves differently. On grounds which we cannot enter here, we have to assume that a small system can by its very nature possess only certain discrete amounts of energy, called its peculiar energy levels. The transition from one state to another is a rather mysterious event, which is usually called a quantum jump. But energy is not the only characteristic of a system. Take again our pendulum, but think of one that can perform different kinds of movement, a heavy ball suspended by a string from the ceiling. It can be made to swing in a north-south or east-west or in any other direction or in a circle or an ellipse. By gently blowing the ball with a bellows, it can be made to pass continuously from one state of motion to any other. For small-scale systems, most of these or similar characteristics, we cannot enter into details, change discontinuously. They are quantized, just as the energy is. The result is that a number of atomic nuclei, including their bodyguards of electrons, when they find themselves close to each other, forming a system, are unable by their nature to adopt any arbitrary configuration we might think of. Their very nature leaves them only a very numerous but discrete series of states to choose from. I am adopting the version which is usually given in popular treatment and suffices for our present purpose. But I have the bad conscience of one who perpetuates a convenient error. The true story is much more complicated, inasmuch as it includes the occasional indeterminateness with regard to the state the system is in. We usually call them levels, or energy levels, because the energy is a very relevant part of the characteristic. But it must be understood that the complete description includes much more than just the energy. It is virtually correct to think of a state as meaning a definite configuration of all of the corpuscles. The transition from one of these configurations to another is a quantum jump. If the second one has the greater energy, is a higher level, the system must be supplied from outside with at least the difference of the two energies to make the transition possible. To a lower level, it can change spontaneously, spending the surplus of energy in radiation. Molecules. Among the discrete set of states of a given selection of atoms, there need not necessarily, but there may be a lowest level, implying a close approach of the nuclei to each other. Atoms in such a state form a molecule. The point to stress here is that the molecule will, of necessity, have a certain stability. The configuration cannot change unless at least the energy difference necessary to lift it to the next higher level is supplied from the outside. Hence, this level difference, which is a well-defined quantity, determines quantitatively the degree of stability of the molecule. It will be observed how intimately this fact is linked with the very basis of quantum theory, vis-a-vis with the discreteness of the level scheme. I must beg the reader to take it for granted that this order of ideas has been thoroughly checked by chemical facts, and that it has been proved successfully in explaining the basic fact of chemical valency, and many details about the structure of molecules, their binding energies, their stabilities at different temperatures, and so on. I am speaking of the Hitler-London theory, which, as I said, cannot be examined in detail here. Their stability dependent on temperature. We must content ourselves with examining the point which is of paramount interest for our biological question, namely, the stability of a molecule at different temperatures. Take our system of atoms at first to be actually in its state of lowest energy. The physicist would call it a molecule at the absolute zero of temperature. To lift it to the next higher state or level, a definite supply of energy is required. The simplest way of trying to supply it is to heat up your molecule. You bring it into an environment of higher temperatures, like a heat bath, thus allowing other systems, like atoms and molecules, to impinge upon it. Considering the entire irregularity of heat motion, there is no sharp temperature limit at which the lift will be brought about with certainty and immediately. Rather, at any temperature, different from absolute zero, there is a certain smaller or greater chance for the lift to occur, the chance increasing, of course, with the temperature of the heat bath. The best way to express this chance is to indicate the average time you'll have to wait until the lift takes place, the time of expectation. From an investigation due to M. Poliani and E. Wigner, the time of expectation largely depends on the ratio of two energies, the one being just the energy difference itself that is required to effect the lift. Let us write capital W for it. The other one characterizing the intensity of the heat motion at the temperature in question. Let us write capital T for the absolute temperature and K times T for the characteristic energy. K is a numerically known constant called Boltzmann's constant. 3/2 times K times capital T is the average kinetic energy of a gas atom at temperature T. It stands to reason that the chance for effecting the lift is smaller, and hence that the time of expectation is longer, the higher the lift itself compared with the average heat energy, that is to say, the greater the ratio of capital W to the product of K and T. What is amazing is how enormously the time of expectation depends on comparatively small changes of the ratio of capital W to KT. To give an example, following Delbruck, for capital W 30 times KT, the time of expectation might be as short as 1/10 of a second, but would rise to 16 months when W is 15 times KT, and to 30,000 years when W is 60 times KT. Mathematical interlude. It might be as well to point out in mathematical language, for those readers to whom it appeals, the reason for this enormous sensitivity to changes in the level step or temperature, and to add a few physical remarks of a similar kind. The reason is that the time of expectation, call it small t, depends on the ratio of big W divided by small k, big T, by an exponential function. Thus, little t is equal to tau times Euler's constant to the power of big W over small k big T. Tau is a certain small constant of the order of 10 to the minus 13 or 10 to the minus 14 seconds. Now, this particular exponential function is not an accidental feature. It recurs again and again in the statistical theory of heat, forming, as it were, its backbone. It is a measure of the improbability of an energy amount as large as big W gathering accidentally in some particular part of the system, and it is this improbability that increases so enormously when a considerable multiple of the average energy kT is required. Actually, a big W equaling 30 times K times big T, see the example quoted above, is already extremely rare. That it does not yet lead to an enormously long time of expectation, only 1/10 of a second in our example, is, of course, due to the smallness of the factor of tau. This factor has a physical meaning. It is the order of the period of the vibrations which take place in the system all the time. You could, very broadly, describe this factor as meaning that the chance of accumulating the required amount, big W, though very small, recurs again and again at every vibration. That is to say, about 10 to the 13 or 10 to the 14 times during every second. First Amendment. In offering these considerations as a theory of the stability of the molecule, it has been tacitly assumed that the quantum jump, which we called the lift, leads, if not to a complete disintegration, at least to an essentially different configuration of the same atoms, an isomeric molecule. As the chemist would say, that is, a molecule composed of the same atoms in a different arrangement. In the application to biology, it is going to represent a different allele in the same locus, and the quantum jump will represent a mutation. To allow of this interpretation, 2 points must be amended in our story, which I purposefully simplified to make it at all intelligible. From the way I told it, it might be imagined that only in its very lowest state does our group of atoms form what we call a molecule, and that already the next higher state is something else. That is not so. Actually, the lowest level is followed by a crowded series of levels, which do not involve any appreciable change in the configuration as a whole, but only correspond to those small vibrations among the atoms which we have mentioned above. They, too, are quantized, but with comparatively small steps from the one level to the next. Hence, the impacts of the particles of the heat bath may suffice to set them up already at fairly low temperature. If the molecule is an extended structure, you may conceive these vibrations as high-frequency sound waves crossing the molecule without doing it any harm. So the First Amendment is not very serious. We have to disregard the vibrational fine structure of the level scheme. The term next higher level has to be understood as meaning the next level that corresponds to a relevant change of configuration. Second Amendment. The Second Amendment is far more difficult to explain because it is concerned with certain vital, but rather complicated, features of the scheme of relevantly different levels. The free passage between two of them may be obstructed, quite apart from the required energy supply. In fact, it may be obstructed even from the higher to the lower state. Let us start from the empirical facts. It is known to the chemist that the same group of atoms can unite in more than one way to form a molecule. Such molecules are called isomeric, consisting of the same parts, iso meaning same, and meric meaning part. Isomerism is not an exception, it is the rule. The larger the molecule, the more isomeric alternatives are offered. Figure 11 shows one of the simplest cases, the two kinds of propyl alcohol, both consisting of 3 carbons, capital C, 8 hydrogens, capital H, 1 oxygen, capital O. Models in which C, H, and O were represented by black, white, and red wooden balls, respectively, were exhibited at the lecture. I have not reproduced them here because their likeness to the actual molecules is not appreciably greater than that of figure 11. The latter can be interposed between any hydrogen and its carbon, but only the two cases shown in our figure are different substances. And they really are. All their physical and chemical constants are distinctly different. Also, their energies are different. They represent different levels. The remarkable fact is that both molecules are perfectly stable. Both behave as though they were lowest states. There are no spontaneous transitions from either state towards the other. The reason is that the two configurations are not neighboring configurations. The transition from one to the other can only take place over intermediate configurations, which have a greater energy than either of them. To put it crudely, the oxygen has to be extracted from one position and has to be inserted into the other. There does not seem to be a way of doing that without passing through configurations of considerably higher energy. The state of affairs is sometimes figuratively pictured as in figure 12, in which 1 and 2 represent the two isomers, 3 the threshold between them, and 2 arrows indicating the lifts, that is to say the energy supplies required to produce the transition from state 1 to state 2, or from state 2 to state 1, respectively. Now, we can give our second amendment, which is that transitions of this isomeric kind are the only ones in which we shall be interested in our biological application. It was these we had in mind when explaining stability on pages 49 to 51. The quantum jump, which we mean is the transition from one relatively stable molecular configuration to another. The energy supply required for the transition, the quantity denoted by capital W, is not the actual level difference, but the step from the initial level up to the threshold. See the arrows in figure 12. Transitions with no threshold interposed between the initial and the final state are entirely uninteresting, and that not only in our first biological application. They have actually nothing to contribute to the chemical stability of the molecule. Why? They have no lasting effect. They remain unnoticed. For, when they occur, they are almost immediately followed by a relapse into the initial state, since nothing prevents their return.